I'll be your event host today, David Block from Domino Data Lab. And today we're going to be talking about the need to think about model management and monitoring in the enterprise. We're also going to introduce the partnership between Domino Data Lab and Amazon SageMaker and show you some of the features that make these two things fit really well together in your entire ML orchestration layer and workflows. I'm joined by a ton of really good guests today, and we're going to give them a chance to do introductions. And at this point, I'd like to give Kirk the floor to talk about his role and a little bit about himself.
Thank you, David. It's really great to be here today. Give me the thumbs up if you're hearing me. So it's working, yay.
I can hear you.
So today I am actually speaking from an office, which I haven't been in over a year, with the new startup that I'm working with called Data Prime. So I'm the chief science officer there. So my background, my far background is astrophysics. I worked 20 years at NASA doing astrophysics research and working on data systems. So I was always surrounded by data. And as the years went by surrounded by data, I became more interested in this thing called machine learning and data science. And about 20 years ago, I left NASA to go become a professor of astrophysics at a university, taught there. After a number of years doing that, I moved on to a data scientist role at Booz Allen Hamilton, doing strategy consulting across all different industries and sectors of business and government. And so I've got a wonderful experience in the science field, both in startups and big companies and in government labs. And so I hopefully bring some value to the conversation today around all those things.
Wonderful. And Rumi, if you could introduce yourself, please.
Sure. My name is Rumi Olson. I'm an AI ML partner solutions architect at AWS. I'm going to run a demo for the joint solution that we came up together that really leverages both Domino solutions and some of the AWS services.
And last but not least, Pawan, if you can give an introduction for yourself.
Sure. Hi, everyone. My name is Pawan Deshpande. I'm on the product team at Domino. My areas of coverage are model ops. So this is everything from taking your model to production to once it's out there in the wild, including monitoring. So I'll be presenting our solution here on today's webinar.
Thanks, everyone. Just to set the scene of Domino Data Lab, so our mission statement is to unleash the power of data science to address the world's most important challenges. So we run a suite of technology that accelerates your ability to deliver data science at scale. Do so with the freedom and flexibility to use your tools of choice, including tools such as SageMaker, and do so in a way that really allows you to think about the management and monitoring of a lifecycle post-production and deployment. And talking about our partnership with AWS, and as you'll see today, we can orchestrate many different data science services. So we're able to orchestrate AWS capability through our platform. And the advantage of that is we also have a system of record for enterprise data science lifecycle management. So all of the context, the why that you're developing a model, not just the what, becomes available, and all of the activity management and tracking. This allows you to really get some consistent capabilities across your entire data science lifecycle and speed up your ability to deliver more models at scale. We have many joint customers with AWS, and we find working with their solutions gives us a real good punch in terms of scalability and solution design. So today we're going to be talking about building resilient model lifecycles, and we're going to be using the COVID-19 situation to set the scene. Being a very dynamic situation that has really impacted the way that businesses operate, and due to that, the way that models operate. So at this point, I'm going to drop the slides, and then I'm going to bring Kirk online, and we're going to walk through some fireside questions. The idea of this is to set the context and the scene for what's important, and then we'll be moving into our demos. So we're going to start with the elephant in the room today. We're going to start with COVID-19. It's the big, scary, and still present thing in our worlds that obviously has a massive impact on the way that businesses operate. That's transferred into a massive impact around things like data set drift and monitoring drift. So we think about shopping patterns or transportation patterns. That has a big impact on the way that we're operating. It's led to some pretty significant failures in model design as well. So can you talk our audience through data set drift and model drift, and why it's very important to think about these as you're designing and developing models?
Yeah, absolutely. I think the fortunate or unfortunately, it gives me a chance to bring up some of my physics background, because when I think of data science modeling or machine learning modeling or any kind of modeling, it's really about mapping, right? So you're mapping an input to an output. So the model is the thing that does the mapping, right? So you try to figure out how do I map these inputs to these outputs. So if we're building a predictive model, for example, of customer shopping, we have a model of what patterns people have, different times of year, different products, different types of weather, different types of places they live, even time of day. Are they at work? Are they at home? Are they on vacation? Are they working? So all these different inputs lead to a predictive output, a model, right? So it's just basically an X models maps to Y. So what we've seen in the last year is there's been drift in the X, okay? So there's something happening with the data, the input to the model, right? But there's also something happening with the Y, that is the outcome, that it's a predictive thing does not match to people's circumstances during the COVID era. People are now working from home. They're shopping for different kinds of things. So it's no longer predictable really what is going to happen based upon where someone is working from. Everyone's working from homes. It used to be if you were on a computer that was identified as your home computer by some way, you were at home, maybe not working. So when I think of model drift and concept drift, a model drift is those two things. It's data drift and model and concept drift. That is, is there something changing in your input data? Is there something shifting in sort of the output variable you're predicting? And so that's really been the fundamental sort of challenge for data science teams, is to deal with that model drift, which has those two separate components. So not only tracking model drift itself, but then to break it apart. Well, is it the data that's changing? Is it the thing we're predicting that's changing? And in fact, it's all of the above. And so it's an intricate problem that data science teams have been challenged to solve in the past year.
Great points. And I think one of the things that you touch on there is it's not enough to now just deploy a model, right? You can't think of models in absence of what's going to be happening in their life cycle. So if you're just deploying code and you're not thinking about the management and ongoing maintenance of these models, you're setting yourself up for failure. Would you agree with that?
Absolutely. I think we've gone past the stage, long past the stage now, where we just have doing data science, what I would call in the sandbox, right? At sort of the birth of the big data revolution nearly 10 years ago, companies said, oh, they discovered that they had data, right? Everyone was collecting data. Then all of a sudden they woke up one day and they realized what hell of a lot of data they got. And they said, what can we do with this data? And so they basically unleashed the data scientists to go play with data in the sandbox and come up with cool toys and cool models. Well, we're sort of past that stage because we're really talking about sort of a world-changing and life-changing and very personal and very sort of risky types of things. For example, loan applications or insurance, unemployment insurance applications. There's been a tremendous amount of fraud in those areas. And so there's got to be a lot of change in sort of the ways those things are detected. The loan application systems, the financial application systems, fraud detection, and also maybe changing the rules a little bit of who you give a loan to, because people's needs are drastic during this era. So you have to be more relaxed in those models while at the same time not letting the fraudsters through the gate. And so now you can't just like say, I have a model that predicts fraud and then just walk away and go do something else. You have to monitor that because it's a changing environment that we're in, changes by the day. Because a government announces a new program and suddenly there's all kinds of people applying for that. And in the mix of all those people applying for it, there's nefarious people who are trying to get that benefit. And I'm a victim of this. I mean, someone actually twice actually applied for unemployment benefits in 2 different states under my name, and I'm actually a plaintiff in a case in California, actually.
Oh, wow.
With some pretty famous people, because I'm actually very well known on Twitter and social media. And so when I talked with the investigator, he said, "Oh, you're in the same list as all," and he named a bunch of extremely famous people in California. And so literally. Even as sort of new things happen every single day, you have to go back and monitor your model to see is it still valid? Is it still doing the right thing?
Yeah, great points. And in your position, like you've been through so many different data science teams and leading them in a number of different ways, and also educating data scientists on this. What are some of the hallmarks you've picked up around where teams are not well placed to think about the ongoing burden, like the monitoring, the management, model set drift, and data drift?
Well, I've always said this, and that data science is not a thing to do, it is a way of doing things. So one of the biggest mistakes companies make is put their data science teams over in some corner over here. Say, there's the data science team, they're doing data science over there. All right, and whatever they're over there might be, it might be just in the IT department, or it might be in the marketing department, or it might be somewhere else. But it's not, it can't be over there. It has to be the business. The business is data. The world is digital. Business is data. You're informed by data, you make decisions based on data, you derive value from data, you create new customer opportunities, new market opportunities from data. It's all about the data. And so the first mistake is having the team sort of aside from the business. Another big mistake is not incorporating business domain experts as part of the team. People who actually understand the business. What is the business proposition? What is our value proposition to our customers, to our stakeholders, to our investors? So understanding the business, it's not just about the math and the coding. Yeah, that's cool. A lot of data scientists get trained in math and coding, and they're brilliant data scientists, way more brilliant than me when it comes to those specific skill sets. But they don't necessarily have the boots on the ground with the business and with that business customers to know what it is that really matters, what really works well. And sometimes the simplest algorithm can create enormous value. I mean, I've heard of a company that basically saved $1 billion in one business quarter just by using something that children learn in grade school, counting. Okay? Yeah. They just basically used counting. They basically counted the number of visits to their site of a particular type of business they were in, and they were able to identify customers who might be taking their business elsewhere because they determined just from the number of clicks to specific parts of their website, they realized the customer was just basically shopping around and not really necessarily interested in buying. And so if they were a prior customer and they were doing that sort of like, they were basically doing things that looked all the world like they were just doing comparison shopping, you realize that customer might leave the business. And so they enacted just a very simple counting algorithm that the customer who passes a certain threshold, which we all can understand what a threshold is X bigger than 10. Okay, if X is bigger than 10, you do something. So they reached out to the customers, and they estimated in the first quarter they saved their business $1 billion in customers. Now you might say, how can one single business do that? Well, it happened to be a $1 trillion company, and yeah. So what's $1 billion? Well, it's a lot, okay, to anybody. And so the idea is to realize that the business value is not necessarily the same thing as the mathematical value of your algorithm.
It's such a great point. I think in the day and age we're in the age of algorithms. Model-driven businesses are competing better than peers that aren't as model-driven. But the trap in that is we tend to think of everything needs to be deep learning or something that's above and beyond the complexity of maybe the problem at hand. So I love the point you make about really understanding the business problem and tracing that through. And I'm sure we're going to touch on that in a little bit. We've talked about the need to think about monitoring models. Once they go into production, they become a pretty important asset. And you gave a great use case about credit risk and how when these are in play, they're actually impacting human decisions. So how do businesses get better at monitoring their models? And also how do they get better at that understanding that layer of models around maybe explainability and interpretation on what the actual business impacts are going to be once it's deployed?
Oh, that's a very rich question. I want to start answering with an example.
Sure.
An example I heard recently of a food delivery startup. Okay, so maybe not a startup anymore, but a food delivery company. I won't name them, but their idea is that people, company, let's just say restaurants. Someone can order food from a restaurant and it can be delivered by this food delivery startup. All right, so they had a call center with 80 people in their call center at this food delivery company where people would call up and maybe complain about their delivery or to place an order or to upgrade their account or something. All right, and all of a sudden during the COVID period, everybody was ordering food from home, right? Very few people were going to the stores. And so this company had a predictive model of how much staffing they needed on different days of the week. For example, more staffing on the weekend or on Friday nights or something like that. And their staffing model just went completely berserk. Their staffing model predicted a certain amount of people they needed to hire or to bring on duty different times of day, different days of the week. And they had a total pool of 80 people they were drawing from for this. Well, once COVID sort of just went berserk around the world, this company was hiring 100 new call center representatives daily.
Wow.
I mean, they basically ran their entire business on 80 people, 80 call center representatives, and they were hiring 100 new representatives every day. All right, and so that's where their employment model, their service model, everything about their model was just completely not right anymore. I mean, it just fell apart. That was the clearest case of a model falling to pieces rapidly. And so the whole idea is we have to understand what goes into so again, that explainability is very important. When we think about the things I said earlier about the model drift has both the data drift part, the X drift, and the concept drift, the Y drift, that is the input and the output. So if you have explainability, you can understand how X is mapped into Y. So if something is changing on one side of that equation or the other, if you know how X actually maps to Y, and that's what explainability is all about, it gives you that insight on how you can start adjusting your model and making it actually work better, get over its brokenness. And so during the past year, we've seen a lot of growth in things like MLOps, okay, so machine learning operations, which incorporates this type of observability and explainability of models, but even more importantly, it basically is more accountability. That it's not just somebody deployed a machine learning algorithm in the company and you don't even know who did it or what's in that algorithm. There's a platform, there's a way that you basically provide what we would call in the data world provenance, something like what was the source of this model, who built this model, what are the components of it. And so if some particular component needs upgrading, you know how to trace it back to who did it and what part needs upgrading. So there's accountability, traceability, visibility, but the word I like the most here is observability. So in the past year, there's been a lot of discussion of observability, and at first I sort of ignored it because I thought it just meant monitoring, like model monitoring. But observability is a strategy. So I like to say, people, monitoring is what you do, but why you do it is observability. You have an observability strategy. So what are we monitoring? We're monitoring the data input, we're monitoring the outputs, we're monitoring the models in between. Is it using the right data? Is it producing the right predictions? And so in some sense, if you're training the model on things that don't exist anymore, that is, people no longer working at work, that is in office buildings or working from homes, there's a completely different set of things that you need to know about to basically recommend products. Because if I say everyone's working from home, all of a sudden that changes the equation of what I recommend. If I have an e-commerce store, what I recommend to people when they're shopping from their home computer. And so it completely changes the model. And so being able to respond to all these things, you need to have some way of monitoring, observing what's going on. And observability as a strategy, again, says, well, where do we place the monitors? Where do we place the sensors, so to speak? So I like to think of it as very meta. That is, it's machine learning monitoring the machine learning. Okay, so we're actually applying our principles of monitoring and insights discovery of machine learning applied to the machine learning models themselves.
It's funny you mentioned that, because we as data scientists use metrics and understanding of observable patterns and behaviors to write these predictions. But also we as data scientists are really bad at using metrics to track our own performance, and particularly our performance of models, right? It's a constant repeated thing. So what are the best metrics to think about? Now, this is quite a broad topic because, as you mentioned, observability is going to rely on the use case or the model case. But what are some of the high level ones? What should we be tracking and measuring when we think about monitoring models?
Well, certainly the data drift is a clear thing, and I think in some of our demos this afternoon or morning or wherever you happen to live, some of the demos are going to talk about some things for monitoring data drift. I mean, there's one that I think we're going to see called KS drift or KS test, which is a Kolmogorov-Smirnov test, which I actually learned about in astrophysics decades ago. So it's basically testing whether two data distributions two samples are drawn from the same underlying data distribution. And I think we can find out right away whether or not the samples we're using to train the data are really the same as the samples of customer behaviors or product behaviors or system behaviors that we see today. And so, so you can start doing these statistical tests on whether or not the data are really representative of the same underlying population. And also this, and also with the on the other end of sort of the concept drift and the model drift is just starting to measure let's just say very in simple terms, just sort of like false positives and false negatives, right? Okay, so if you have an e-commerce store and you have a recommender engine, and you recommend products for people, and let's say people are clicking on the product and buying the product, all right, and you might say, well, that's successful, but how many didn't click it? Why did they miss? They were looking for something else, and so you have to start exploring. What if I change in some way the recommender engine to have more diversity in what it's recommending, and then see if some of those more different types of recommendations than what my algorithm would traditionally suggest. See if maybe people are now clicking on those, accepting the offer through that the recommender engine is offering. And so you can start testing to see if you're actually missing things. Because you might say, wait, we have really high accuracy here, but how do you know that's high enough? Or maybe there's something else happening. And so being able to do more sort of testing. So I think it's always been said that a data science culture at a company means it has a culture of experimentation.
Yeah.
Because really data science is a science, right? So it's experimental science. And so I always tell people, people sometimes confuse machine learning with data science. I said machine learning is just the algorithms, the mathematical algorithms that identify patterns in data and describe patterns in data, make you able to build predictive models. But the data science is the scientific process of discovering through experimentation which of those patterns actually bring value to the organization, which patterns actually give you real insights that mean something, and which ones maximize the insights and optimize your operation. And so we need to make sure we're not forgetting about that culture of experimentation that helps us to test whether we're producing the right outputs from our inputs.
That's such a great point. We are built around experimentation and exploration, and that comes with its own pitfalls, right? We have to have freedom and flexibility to operate. We need to be able to look at problems. But one last question for you. I could talk to you on the subject for hours, I'm sure. But one last question for you, and it sort of talks about data set drift. And quite often data quality issues exist in upstream data applications. Now, they might be seen in monitoring systems as an example of data set drift, when realistically we've just got a quality pattern failure that we need to address. What are some of the best practices for differentiating between, say, data set quality issues versus actual data set changes and patterns and trends?
Well, one of those techniques is just going back to my domain expertise statement. That is, you need to have subject matter experts. And I like to tell a very short story of my early days at NASA 30-something years ago. I was in charge of doing some work with a database, and I had never worked with databases before as an astronomer. This was 30 years ago. Databases 30 years ago were only in banks, right? We were permeating the world. And so I was just working with databases, and one of my roles was to determine how many scientists from different parts of the country were using this national treasure, this telescope, which 6 billion of your US tax dollars, your dollars, paid for this telescope. And so the people in Congress wanted to know what was the distribution of scientists across the different states. And so I learned some SQL and learned how to query the database and find out, count the number of unique states, the number of scientists from each state, ordered by state. And I discovered in doing this that there were 93 states in the United States.
Wow.
Well,
there's not 93 states.
There's actually 50, right? And what was happening was there was all kinds of misspellings, like Mississippi was spelled multiple ways. I won't even talk about Massachusetts, how many ways that was misspelled. Connecticut, oh, there's another one. New York was one word, two words, uppercase, lowercase. I mean, all those things counted as a different, unique state. Well, I was able to solve that data quality problem because I actually knew the right answer. I actually knew that there are 50 states in the country. But what if I was doing something else, like how many unique products sold last month? And if I do that query to the database and it says 17,023 unique products sold last month, how do I know if that's the right number? I mean, I really don't know. I mean, it's just so as a data scientist, I need to talk with a subject matter expert in the business to say, well, hell no, we only have 8,000 products. How can we have 17,000 unique products? And so so one data quality issue is sometimes just doing sort of like what I call data profiling, which is having data profiling. I just say having that first date with your data. So have that first date with your data. Look at the outliers. Look at the min-max values. Look at the ranges. Look at the data histograms. Look at the distributions, scatter plots, to see if there's something odd or unusual. But at the same time, have those conversations, with the business domain experts, and says, does this make sense? Do these numbers make sense? And so I think those are two sort of subjective and objective approaches to addressing the data quality issues.
Kirk, that was a great bit of perspective, and from behalf of our audience and also from Domino Data Lab, thank you very much for participating in this chat, and I'm sure there'll be more questions at the end. Now we're going to move to our demo portion, so I'm going to bring in Rumi, who's going to take us through how AWS and Domino Data Lab work together. Rumi, I'll be handing over controls to you now.
Thank you, David. So before the demo, first, I'm going to go over very quickly about SageMaker, Amazon SageMaker, and SageMaker Autopilot. Then move on to the solution architecture that leverages both Domino's solutions and some of the AWS services, including SageMaker Autopilot. And then I will demo that part of the solution and show you how things are put together. So let's begin. So Amazon SageMaker is production ready with robust IT ops features across security, workflows, scalability, and orchestration. So SageMaker is a service with a lot of different features and capabilities in it. We typically talk about those capabilities as falling into 4 categories. Number 1, data preparation. 2, the model build phase. 3, training and tuning. And 4, deployment and management or hosting. So these 4 categories really address the needs that machine learning builders have when dealing with each stage of a model lifecycle. Today, I'm going to focus on SageMaker Autopilot, which is a part of a solution architecture I'm going to go over later. So Autopilot is an option to automate the experimentation process. Autopilot takes a tabular data set as an input and uses AutoML to deliver an optimized machine learning model for regression or classification problems. And Autopilot automates data analysis and generates potential training pipelines that explore a variety of feature engineering steps and algorithms. It performs hyperparameter tuning, model evaluation, and then ranking of the results. So now let's look at dataset and use cases. We are using bank marketing dataset from UCI, which is a typical introductory task in machine learning, like the Hello World equivalent. The use case of the dataset is to predict whether a customer will enroll for a term deposit at bank after 1 or more phone calls. So here is what the overall solution architecture look like. Starting from the dataset saved in a S3 bucket on the upper left, the dataset gets loaded onto Domino's platform and perform a simple data prep work on a notebook. Then launch an autopilot job on the platform. And the autopilot job will further analyze the data, expose feature engineering steps and algorithms, and it performs hyperparameter tuning, model evaluation, and the ranking of the results. And then we create a SageMaker endpoint from the best performing model. So that once the model is deployed and online, we will use a Lambda function to call the endpoint through invoke API. The inference data saved in S3 will trigger the Lambda function and execute the code to call the API. The results of the inference will be saved back to in S3 as a CSV file. And then CloudWatch events trigger another Lambda function once a day, or whatever the interval you specify, to upload the inference data, and that is saved in S3, and to Domino Model Monitor, DMM. So you can see the model drift and starts on DMM. And then finally, when the drift is detected, DMM sends a notification to an email. So now let's move on to Domino's platform to take a look at some parts of the solution architecture and how autopilot job and model endpoints are created on the platform. And then we will go over how Lambda functions call SageMaker endpoint. So before taking a look at the code on a notebook, I will show you how to set up access to your AWS account from Domino's platform. First, you go to settings right here, and then set up an environment variable. So you can see here. The most important part here to point out is the AWS access key ID and AWS secret access key. Just to spell out like this with underscore. And you can set those keys. We can get those keys from your own AWS accounts, IAM role. Once that's set up, let's move on to the notebook. Scroll up a little bit from the beginning. So there are a lot going on in this notebook, but I will point out the parts that are important to call out. So looking at this cell, number 3, the number 1 is security. Security is job 0 at the AWS. As you can see in the code, in this environment, we use an STS token. and an IAM role for access permission control. And then you set the S3 bucket right here, and that is saved as an environment variable. This is just retrieving the value from the environment variable. And moving on to the next cell, you download the data to Domino's environment. And then we are going to split the data set, which is right around here, to train and test data sets and upload them to S3 so that the autopilot has access to this data set. And then let's move on to where we create the autopilot job. So first, we need to set up a configuration for the job. So this is where that happens. So we specify where the data source is in S3, as well as the output location, as you can see, which is also S3 path. And you can optionally specify a type of problems you want to solve with the data set here in this configuration, or you can let the autopilot choose for you. And then, as I mentioned earlier, autopilot can build regression, multi-class classification, or binary classification model. For our data set, right choices, binary classification, it's pretty obvious, but let's leave it blank for now and then let autopilot choose. Next, we launch the autopilot job right here. So this is where the autopilot job gets created by calling create an AutoML job and pass in the configuration we just created in prior. So now let's move on to SageMaker Console. After that, the cell that I just showed, the code that I just showed is executed. Autopilot job creates multiple jobs on SageMaker Console. So the first one is processing jobs. As you can see, this SageMaker Console, processing jobs, you can choose from here to go here at the same place. And by just the way we created the AutoML job through the code, it creates 3 different documentation dash, PR dash, DB dash. Those 3 jobs gets automatically created. And then another job that is automatically created is hyperparameter tuning job. It's right here. So you can go from here, see training, hyperparameter tuning jobs. And this is the one that's created. And that has been already completed, but as you can see, it took almost 10 hours to complete. And for this hyperparameter tuning job, 250 training jobs are created and experimented with different combination of hyperparameters. So you can see here, this is each job that this hyperparameter tuning job created. This is a training job. And you can also see through the training jobs here, the same jobs as listed here. And those are all completed. And as you can see, the duration is, each of them is 2 minutes, 3 minutes, pretty short. And with the performance metrics, I believe this one is F1 score that's being used. And then you can see how well this particular combination of hyperparameter it's produced. This one is 0.57, 0.94, and so forth. So now let's go back to Domino's platform to take a look at the results. So after 10 hours, results gets returned, and you can view that by using describe AutoML job. And by calling the API, this is what you get. This is a little bit hard to see here because but then this is a JSON file. And within it, you can extract just the best candidate. So which one performed the best as far as F1 score goes. And then by printing that value out, you see this particular training job performed the best with a 0.955 F1 score. So now we will deploy the best performing model. So this particular candidate and then in order to deploy the SageMaker, deploy as a SageMaker endpoint, we call 3 APIs. The first one is create model. So this creates a model object on SageMaker based on this particular candidate that we chose. And then after the model object is created, we are going to create endpoint configuration, say which type of instance type we want to deploy it on, an initial count, and so forth. This initial count, so this can start as the endpoint. It can start as the one instance, or you could start out as multiple. But then underneath, SageMaker endpoint automatically auto scale based on the number of inference calls being made. And then finally, with that configuration information, you call create endpoint, and then that will deploy the best candidate model for you. So now let's see. Let's go to see the SageMaker console and make sure that endpoint has been created. So to find where the SageMaker endpoint is, I go to inference and then endpoints. And then you see this model endpoints being created with this name that we specified from the API call, auto ML banking. And then make sure the status is in service. If we take this name, auto ML banking, and data that's been created, it automatically assigns a name for you. And we take this value and bring it to the Lambda now. So moving on to the Lambda console. So let's see. So we can start from here. See, so this is where endpoint name it's retrieved from the environment variable. So environment variable can be found on the configuration right here, environment variable. And this is where the auto ML banking, this endpoint name, and then my S3 bucket, and then where the data set is saved. And then, as I mentioned earlier, when I was walking through the solution architecture, that this Lambda function is triggered by S3 event. So in this case, the event is when as you can see, object created by the put. So when you upload the inference data to S3 bucket, and that event triggers to execute this Lambda code. And in this code, and this is where all of the environment variable is basically the value is retrieved into this code, and then the event that's triggered from the S3 passes the value from here, and you basically just retrieving the object key and so forth in order to get the actual file, the inference data. So the inference data, using the inference data passed on from the S3 bucket, we are calling invoke endpoint to the model endpoint right here, specify model endpoint name, and then sending that inference text into it to produce a prediction. And returns a response, and over here it's just a parsing to get the actual results back. So results in this case, yes or no, and then that is over here. It's just basically put together into it's another CSV file, so that we can save as a CSV file temporarily in Lambda's local temp folder. Since Lambda it doesn't keep this code nor what's saved in temp, hence the name temp. We have to make sure that that gets persisted somewhere. So we upload the file, this temp file, into S3. So that's the code that happens here.
Just a quick verbal time check, Rumi.
Okay. So last thing, just very quickly, I'm going to go over is this last function. So this is the Lambda is triggered by S3 CloudWatch events, so excuse me, once a day to send the prediction data to DMM. So there are a number of environment variables that hold data like DMM URL that specifies to where you send the prediction data, and then DMM API token, which is to make sure only permitted party can send the data to the URL, and then model ID, which specifies which model on DMM we are sending the data to. The rest is pretty simple, HTTP request call using Python library. So with that, I will hand it over to Pawan, who will walk you through DMM once the data is received from Lambda. Pawan, the floor is yours.
Great. So I was going to give you a quick overview of Domino Model Monitor. So if you're already familiar with Domino, our Domino flagship product, that's our Domino Platform, that's used to ideate, build, collaborate models. You have access to scalable compute resources. So that's really to build your models, publish and host them. And then we have a second offering, which is Domino Model Monitor. And this is used to monitor production models, visualize and diagnose issues, receive alerts and notifications. And that's really what I'll be showcasing here today. These are part of a larger product suite for an end-to-end solution for the entire data science lifecycle. And the reason we built this product is we have repeatedly heard from our customers around challenges around the lack of model monitoring. The specific challenges we hear are from business leaders. They often don't understand the business risks that they're incurring by having models in production that they're not monitoring, that could have degraded, and they just don't know what's happening. Data scientists, if they are monitoring, often they'll do it in an ad hoc nature. So they may be writing their own custom scripts to do monitoring, and it's taking their time and energy away from doing their core job, which is to build really good data science models. And then the third kind of group that we've heard challenges around monitoring from is model ops. These folks, they often feel blind. They're blindfolded. They don't have visibility in terms of what models in production and the health of those models. And DMM is built to satisfy all three of these challenges. Currently, organizations that we see, in terms of how they deal with drift, a lot of them kind of pray and hope for the best. So they deploy models in production, they just assume they work and just will keep kind of the shop running. The second camp are folks who retrain their models periodically. So they'll continually retrain their models with fresher data, they get new ground truth data, retrain their models, and they're mitigating the drift, but it still does occur. It's occurring for a shorter period of time between retraining runs. But not all organizations can retrain their models very periodically. The third group we see are folks who are doing ad hoc tests. So here the data science teams are building their own custom scripts to track drift. And the challenge with this is often is inconsistent from model to model, from data scientists, from team to team. There are different implementations, different ways of measuring drift, and there's no consistency or an easy overview to see how your models are doing. The second thing is these are often not run in a continuous process. They're often run on an event-driven basis. So a data scientist may anticipate that there's drift occurring, or there may be some downstream business loss, and then they will suspect that drift may have occurred, and then they'll run the test. So they're not run continuously, they're run ad hoc and not on a regular interval. And the fourth way is continuous and standardized monitoring. And that's really what DMM is built for. So it's always running behind the scenes. It's standardized across the whole organization, across all your models, across all data scientists and teams. Typically, when we talk about monitoring with regards to data science, there are kind of three types of monitoring that come to mind. The first is cost monitoring. So this is looking at how much dollars and cents cost it takes to host your models and perform inference. The second is ops monitoring. So this is looking more at resource utilization. So like memory, disk usage, latency. And these first two are already handled. There's a lot of existing tools in the market. AWS has a lot of built-in capabilities to do cost and ops monitoring. What we're really focused on with Domino Model Monitor is data monitoring. And this is a new and not so easy problem. We're focused on data drift, model quality, and data quality. And the reason this is challenging is that if something fails, it often fails silently and will continue to make predictions even though it's not performing well. Whereas for cost, you'll notice a big spike in cost, for example. Ops, you'll notice your server's falling over, it fails very loudly. Data monitoring is often silent and will continue to perform normally, but it's actually not behind the scenes. And so in terms of how our drift detection works, we read in data from 3 different data sets. So first, you provide the training data. So this is, for example, a distribution of values for a particular feature. And then you also provide the prediction data that you're performing inference on. So this is the distribution of feature values for a particular feature that you're performing inference on. So what we do is to compare these 2 distributions with each other and perform a statistical divergence test, and we're able to determine how much it may have drifted. The second class here are the output labels coming out of our model. These are the prediction classes. So this is a binary classification model on this slide, for example, and then the actual ground truth data. And using that, we can compare them against each other and generate model quality metrics. And I'll showcase what that looks like in product today. In terms of how Domino Model Monitor works, it's a black box. It sits outside your production models, and these models could be developed in any platform, hosted on any platform. DMM is really agnostic to what types of models there are, where they're hosted, how they're built. Really what we need is the input data that you're providing to your model to perform inference. You send a copy of that to DMM. And then the output labels coming out of the model. So as it generates output labels, a copy of that is also sent to DMM. And then you also provide the training and ground truth data if and when available. Based on these 4 pieces of data, we're then able to provide reports and visualization in a web app that will show you momentarily, and also alerts to all the different stakeholders. And this is not just data scientists. So the key takeaways and kind of the core value proposition of the Domino Model Monitor is that it provides proactive and actionable monitoring. It's continuous and it has shared visibility, so it's not just for data scientists, it's for kind of anyone who's concerned about drift and model quality. And then the last thing is we've really been building this for enterprise scales. We have very large organizations and customers, so this has really been battle tested at a large scale. So with that, I'm going to dive into a demo of the actual product. Right. So we're on the home screen of Domino Model Monitor here, and as you can notice, this looks kind of like a lightweight model registry where you can see all the different models that have been registered in Model Monitor. You can see the name of the model, if they're a classification or regression model, the version number, the date they're registered. Next to that, you can also see if they've been passing or failing the drift check. So on a particular day, you can see which tests have passed and which ones have failed. Similar thing for model quality here. And then you can see the prediction traffic as well. Next, I want to dive into how we would register a model. This is done programmatically in the demo that Rumi showed, but I want to show you a visual example so you can see the components that go into Domino Model Monitor. So I'm just going to put in a sample name for a model, put in a version number here. I can specify it's a classification or regression model. So this is classification, for example. I'm then going to add training data. So in this case, I'm going to point to a S3 bucket here. And as I mentioned, this can all be done programmatically, and that's what most of our customers use, but just for demonstration purposes, I'm showing you how this is done in the user interface. So now I'm specifying a CSV file that contains training data. And based on this, DMM is now reading that CSV data, and it's automatically inferring each column type. So it's trying to guess if things are a feature and what value type they are. And it's done a pretty good job, as you can see here, but there are a couple of corrections. So for example, Y is actually the prediction, and date is actually a timestamp. And then based on this, we can go proceed forward. It generates a JSON file, and this is what Rumi was actually generating when she registered the model in DMM. But you can do this to the UI as well, and you go ahead and register the model. For the sake of brevity here today, I'm not going to walk you through the rest of the process, but it's a similar process for registering ground truth and prediction data as well. Next, I want to deep dive into one of the models and show you an example of drift here. So we're looking at this customer churn model here, and we can see over time if it's passed or failed in different drift checks. And then we'll go down a step deeper and actually look at on a per feature basis what's going on. So we can see all the different features in this model, and we can see the training data distribution, the prediction data distribution. Kirk mentioned a bunch of different divergence tests, and many of these we offer out of the box here, so you can choose which one you'd like to use, set thresholds for alerts, and then specify if you'd like to receive alerts on that. Next, I want to go into a specific example of drift here. So we can see contact. This is how customers would like to be contacted on their telephone number or cell number, for example. Let's say this example here. We can see in training this kind of roughly kind of a 50-50 split between telephone and cellular feature values. But when we actually look at the prediction data, there's a large class asymmetry. So there's a lot more prevalence of cellular data. And so that shows that our training data is asimilar to our prediction data. And so this is a cause for drift here. And we can see that reflected in the drift check going off here. Another example here, this class here, we can see, for example, the distributions are different from each other. So this appears in production, but not in training data. But also notably, there's untrained classes. So there's classes that are actually showing up that didn't show up in training, and that is also a cause for drift as well. So these are the types of things that DMN picks up on, and will notify you instantly if something occurs that you can go and then investigate and remediate it. The next piece here is model quality. So it's very similar to data drift in that we're tracking the comparison between the output prediction labels and the ground truth data. And on a continual basis, we're tracking all these different metrics: accuracy, position, recall, F1, and others over a time series. And if something crosses the threshold, you can instantaneously receive an alert for that. And then below, you can see the generated confusion matrix here as well. So that's a quick whirlwind tour of Domino Model Monitor. I'm going to pass it off back to David to wrap things up.
Thanks, Pawan. That was an amazing overview of Model Monitor, and we hope you took away some of the key aspects there. Let me just bring my slide back up. So just to land on some key takeaways there, if we think about what Kirk was giving to us in terms of the perspective around why we need to think about monitoring and bring that into the forefront of our activities when we're producing models. We hope you saw with the combination between using SageMaker capabilities and Domino capabilities, you had the ability to orchestrate these different techniques as you were going through these layers, and then provide automated capability around what's happening to your models. So things like data set drift and model drift, and be able to see that in a place that's very easy to see with alerters and everything else. What we hope this allows you to do is scale enterprise data science. So have a standardized monitoring procedure that you know you can trust and rely on, means that more production models are in play and you're not having to think about too much of the technical side of monitoring and managing and keeping those models at scale. So on behalf of Domino and AWS, I'd like to thank you all for your attendance today, and I'd like to thank our speakers. To learn more about the products you've seen, we've got a couple of links in this recording will be sent out, and we will reach out with answers at the end around some of the questions that we didn't get time to. Within the question box itself, there were a few questions that we've answered as well. For a full published technical walkthrough of what you've seen here from the AWS and Domino side, please check out the GitHub account. And for any further support or information, please feel free to contact us below. Thanks very much. Cheers all.